Inclined planes. That's the next topic in this 4U physics video series. So we're looking at free body diagrams on surfaces that aren't level. And so to intro this, Mr. Anderson does a really cool little thing here. I'll show you. If you want to check him out, that's the link. Go like his page, stuff like that. Go subscribe. I'm sure he'd appreciate it. So this is the little, it's just cool. Just watch.
Draw some of those. I want to give you a thought problem. Imagine we have a scale on a platform and you just simply stand on it. So we figure out your weight. What do you think would happen to your weight if we angled that platform? Is it going to remain the same? Are you going to weigh less? Are you going to weigh more? What if we make it even steeper? Well, I tried this. I stood on a scale, and so this is my weight. And then I put it on a platform, and I used my iPhone to figure out that this is around a 17-degree angle, and you can see that my weight got less. And so that seems kind of magical. It'd be a great way to lose weight. But what's really going on there, you have to draw a free body diagram. So I'm the object sitting on a platform. And so
I'm going to leave it at that for now. We're going to do the rest ourselves here. So here we go. Here's Mr. Anderson's results here, his 172.0 pounds. And then on the sloped 17-degree incline, 162.6 pounds with a 17-degree incline estimated by his iPhone. So a couple things we can do as calculations for this. What's Mr. Anderson's mass? Well, what we need to do for that. Obviously, we'd look up the conversion for pounds and kilograms, right? So let's go pounds to, P-O-U-N-D-S, to kilograms. And it pulls up, the other way around for us here, but I think of it as like 1 kilogram equals about 2.2 pounds. It's actually 2.20462 apparently. And so let's work on a conversion for that. So that's the, conversion you could just look up. And at this point then, grade 9 math kicks in where you just have a ratio of pounds to kilograms. We have this known ratio and we have a certain number of pounds, right? So super easy math to work with very systematically. So you don't have to remember, do I multiply or divide and stuff like that. If you look at what you need to multiply by here for this ratio and this, set of ratios here to this to stay true, you have to look at the same multiplication, right? So here, the multiplication I always say is just the second divided by the first. So the one you end up at divided by the one you start at. And so you can tell we're doing a multiplied by a 1 over 2.20462. So multiplied by 1 over 2.20462. And that would give us the weight. Or the mass, actually, sorry. And so that would be the 172, which is really a measurement of force. So it's really weight. And then we're dividing by that 2.20462, or 2.2 approximately, gives Mr. Anderson's mass in kilograms as 78.01, blah, blah, blah. So basically 78.0 kilograms, right? So because we're estimating this one, then we're, essentially think of the significant digit stuff from grade 11. You can't keep 40 decimal places if you're only really measuring to 1 in one of your measurements. So anyway, it's about 78 kilograms. Other things we could ask, what's the force of gravity on Mr. Anderson, to put this in more of a science and physics perspective take on it. So Fg equals mg, and so we'd have the 78.0 times 9.8, and that would give us the number of newtons that Mr. Anderson weighs. So we'd have the 78 times 9.8. I may as well use all those numbers since they're there. That's what engineers do. They keep floating point decimals and then round to the correct number of significant digits later. So we're looking at 764.5762 and so on. So this is where you might say 764.5 or, I guess 0.6 there, right? I was thinking of a 0.5 rule, but it's the other way around. So 764.6. Newtons. Okay, so just some calculations we can do about it. The interesting one that I want to work towards being able to do is, can we confirm the angle of the ramp? Or can we confirm what the weight should be if the angle is at 17 degrees? Are those things that we can do? Well, by the end of this lesson, yeah, absolutely. Okay, so we're going to come back to that stuff. All right, so inclined planes, something for us to look at here. You may have seen some of this in grade 11, but just making sure to do a good job with this here. So I'm treating it as if it's new and give you a bit of a a smaller number of questions to focus on here. Hopefully it helps you get a little bit of a break if you found some of them a little longer, but here we go. So the new thing for this, I've mentioned earlier in the course, is that you assign a reference frame in a little bit of a different way than normal, right? So the best way is to assign a reference frame so the direction the acceleration's in is your x direction, like your positive x direction. Okay, so that's the plus x direction like that. And then the y direction is always going to be perpendicular to that. Okay, so your positive x and your positive y. I don't normally put the positives in there, but that's your direction system. And I meant for that to be parallel. It's just when I'm writing on a smartboard on an angle, sometimes group things together here. Sometimes things get a little, there you go, better. All right, so that's our direction system, right? That way you can just sort of think of the way you're accelerating is the way the force, net force is, and so on, right? Yeah, so that's a good thing to do. And so when we're looking at this, another thing that's good to do is to have sort of that reference frame on there obvious, like that dotted line showing through the angle of the ramp. And then that's going to help you see your components of your forces, okay? So what we have is we have the force of gravity, obviously, on this thing, and we could calculate whatever this is out, and so on. It's just mg like before, but we're just looking at no numbers here for this one. And so if you look at that, then there's a component of that gravity force that is perpendicular to the ramp, in other words, in the y direction, so my FGY, and then parallel to the ramp, my FGX. And obviously that FGX could be written either down here, like my FGX, or just slide that up so that it's from the center of mass as well, like a free body diagram. Should be, it could be, whatever. Nice to have it that way, right? So there's our reference frame stuff that I already talked about, and some other things we'll do shortly. All right. So when you're looking through things here, let's analyze a couple things. The fact that we know the acceleration in the y direction. This thing's just accelerating down the ramp. It's sliding down the ramp. It's not lifting up or down off the ramp, right? It's accelerating along the x direction, but there's no acceleration vertically, and you can tell because it's not lifting up or grinding into the ramp. Okay, so that's a bit of a weird one here that you got to really watch for, is that it's not lifting up, right? So it's not rising up or off the surface of the ramp, right? So I don't know how to. It's not doing any of that stuff, right? And so that means the net force in the y direction, right? F net in the y direction is 0, and so our F net in the y direction would be whatever the forces all are adding to 0. And of course, in the y direction, which just to remind us here is this way right now, right? That's our vertical y direction, perpendicular to the ramp. And so we're saying, okay, well, the FGY is in that direction, and there's also a normal force in that direction. And if there was anything else, we would add those up too, which in this case there isn't, right? But I just think of the net force as like add up whatever there is, so you leave space for all the options. And so we're getting from this that 0, we have the 0 equals, I'm supposed to leave some room for myself here. So 0 equals the FGY, y component of the gravity, and the normal force. And so we end up with what that normal force is equal to by subtracting the y component of the gravity out, right? So subtract that FGY from both sides. And we now know what the normal force is. The normal force is that FGY. If you think back to Mr. Anderson on the scale, Fg was normally his entire force of gravity. Now it's just a component of that force of gravity. So you can see why the reading on the scale gets less, right? So if we were drawing this originally, sometimes they ask you to draw free body diagrams before you know the sizes of things, right? And so you think of that size of an arrow now, and you're like, okay, well, it's going to be the other way like that. And so you go up and you're like, you look at how big it is and you adjust the size if needed. Okay. Yeah. So that's start at it here. So we have a red block sliding or accelerating down an inclined plane with friction. So we're gradually going to work towards having friction in this at this point. And for this lesson, friction is just given to you as a value. Okay. So the free body diagram for this one, there's an extra force involved. Okay. So you look at that and you think, okay, well, the component of gravity must be bigger than the force of friction if it's accelerating down the ramp. That's sort of a thought process here in terms of like how big you might draw that friction force. We're told that it's accelerating down the ramp, so you wouldn't want to have that friction force bigger than the component of gravity down the ramp. Yeah, so basically this free body diagram must be true in this scenario. What would be true if we're told it was sliding down at a constant rate? Well, if it was sliding at a constant rate, this component here, so I just drew it there to match, and I'll just slide it up, right? That component would be the same as this one, right? So we'd have that same kind of picture, but we'd have a big enough friction force that it would be going with constant velocity. We'd have a net force of 0, right? So, oops, that's the other way around here. I'm supposed to do this. Get rid of that. So the component FG would be the same as FF. Let's see if I can just add it a second ago. There we go. So I'm wondering if I can just clone that thing. Probably better off. Well, let's just see. Go to properties. I want to change the transparency here. Getting messy. Hang on. Bear with me while I work with tech things. All right. Get rid of that guy, and I think then I can make this guy transparent. It's easy to sort of put it in there and not block out other things, right? So I'll shrink that down. But basically the idea is we'd have that free body diagram, which I don't have quite enough room for there, but we'd have a matching size here, right? So the size of, see if I can make this make sense with that small of a diagram. I can barely see it on my monitor here. So we'd have that component down and the component this way would match, is the idea. Okay. And then what if it was slowing down as it slides? Well, then you'd want to show, I might just show this one up here since we're working live here, videoing as we go, right? So for, I'll just do this here where these would be the same to be constant velocity, right? So same for constant velocity. And then if we were slowing down, then we'd have, you know, the component this way and this way, right? This would be slowing down. Right? So you have a net force up. All right. Next here we have read the book being pulled up an incline. It's accelerating up an incline. And so free body diagram for that. Obviously, you're going to have an applied force up now and with friction as well, right? So think about the free body diagram for that one. Maybe press pause and try it and so on, right? But you'd have the force of gravity down. You have the component of gravity down the ramp, the component of gravity vertical. Would there be a normal force that would match because the same, you know, this F N equals F G Y. And again, we're doing X and Y components like normal for inclined planes, that is. And what else? So we got that. And then we have an applied force to make sure we have a nice big applied force up the ramp. And then there might be some friction, but it's certainly not enough to add up to, you know, win the tug of war against the big red force up the ramp, right? So there might be a friction force here, right, that's going against things. But if you look at the size of these two things, right, so this component of gravity down the ramp and the friction, they're not adding up to be bigger, right? And so here I've got this is bigger than that, right? So larger, which means there's an F net, you know, up the ramp. Which in this case, maybe then you define up the ramp as positive if you wanted to, right? So you could switch this to be like, this is the positive X direction, I suppose, in that scenario, to make it nicer to deal with so you don't have negatives. But, you know, obviously you can deal with negatives if you have to, right? So there's that larger force and so on. Let's just look here. It's a little bit close. So there's the component that way, hopefully matching looks like that one's gets a little bit too big, right? I want to have these two match vertically, and then we've got the component down like that, and then this force of the friction like that. And so I'm looking at that thinking that might be a little bit too, that's pretty close, right? So I'd probably have this guy even bigger if it's accelerating up the ramp. So things to watch for, I suppose. And then if it was constant motion, obviously they'd match, which looks like more like what it was, to be honest, as it was originally drawn. All right, so example 2, book sliding down inclined plane, 30-degree angle to the ground, and the force of friction is acting, again, just given to you as a 1.5 newtons. And so we're going to determine the net force and the normal force and the acceleration. The normal force isn't really needed right now, but it will be once we're working with coefficients of friction to be able to determine how much friction there is. So watch for that. And of course, with Mr. Anderson's intro here, notice that the normal force is less. And so that's going to affect how much friction there will be, right? So solution as it was worked out here, obviously we know the angle and the mass and the friction force and so on. And we want to know the net force for now, okay? So the analysis here, I want to show you something about, did I do that in a previous one? There was a question here. So yeah, the way they're showing, I do have warning about this later here, but even this one is kind of weird. They're saying like they're not collinear, the vectors aren't in the same direction. So you have to get components of them is all that's saying. And I'll come back to the warning of how they're showing things later. But it says, using geometry skills, you can see that FGY, the Y component, it makes an angle with gravity of a certain value, okay? Well, they have it labeled here, right? Here's the angle to ramp, 30 degrees. And they have that labeled in here, this angle in there, as the 30, right? And I definitely remember as a student sort of being a little bit concerned about identifying that angle, like how to identify that angle. So there's a couple ways. One would be if you look at this triangle here, and you say, okay, well, that's a right triangle, and it obviously has a 90, and it has the 30, and it has another angle. And so at this point, you could say, well, this is also another angle. So basically the 30 and this would add to 90, right? 30 and unknown would add to 90. Well, look right here, you have 30, well, you have the unknown, I should say, and something adding to 90. So basically, based on that, you can just say, well, that's obviously 30 degrees, right? Again, if you made a whole other triangle here, well, then we'd have the 90s there, and this is not the other one, right? And so it has to be this. So I think the way I showed it first was probably better. The other way I like to do as a physics-minded person is I look at the extreme case, right? When the angles are a little closer to 45, it's a little hard to tell because they all look about the same. But if you look at this tiny little angle here, then in this triangle that's happening here, you've got a huge angle and you've got the tiny little angle, right? So obviously the tiny little angle must be the tiny little angle. You can tell like the angle to ramp is that angle that's there, right? So looking at extreme cases, either a really big angle of ramp or a really small angle of ramp, it's going to help you identify which angle is which. 1 second here, got a phone call apparently. All right, here we go. Sorry about that. We've got the force of gravity, and then there's components down the ramp shown there, and components perpendicular. We've got the friction force, we've got a normal force, and we just want to find out all these things, basically, right? So let's just go through it all. So if it wants the net force in the x direction, then we would look at the triangle. We know the 30 degrees is where it's showing there, as I showed earlier. And so the FG is mg, and the mass was given as 0.5, and the gravity was given as 9.8. And so we do 0.5 of the 9.8. It's going to give us 0.5 times the 9.8 gives us the classic 4.9 that you see a lot. Right, so 4.9 newtons. Then FGX here, we're opposite, right? This side here is the opposite side of the triangle. And so in physics, we would say, we just go for it and you have your FG sine theta, right? So this is going to be the 4.9 sine of the 30 degrees, which is really a half. And so dividing by 2 gives us 2.45. That's the x component down the ramp. And we were given the force of friction was 1.5. And so we have F net in the x direction is the force of gravity in the x direction and the force of friction. And so we're going to have the gravity in the x direction is the 2.45. Notice I'm putting that in as a positive because we had the positive direction down the ramp. And then we have the friction force in as a minus, right? It's up. So we have, and I'm just putting here, and we have the friction force. And so I'm putting the friction force in as a correct value. I'm adding that correct value into the system though, okay? So that's the way it's really should be done. We have the negative 1.5 there. And so now really we have, of course, that's just the same as subtracting, right? And so I just prefer not to have someone say subtract friction because I've seen students plug in subtract and then they have the negative number in as well because they had it written up here as a negative number and so on. Okay, so really just think about the directions of things as you're working and should help. So 2.45, take away the 1.5 gives us 0.95 newtons, and that's the net force in the x direction. In the y direction here, y direction, really what we know is that this way there's no acceleration, right? It's not accelerating up or down off the ramp. And so the usual applies here. F net the y direction equals 0. And in this case, it is, of course, the FGY and the FN that are combining there just vertically or perpendicular up and down from the ramp, I should say anyways. And so we have the FGY can go in as the FG was 4.9 and we're adjacent to the number. So we're going to do cosine of the 30. And so I may as well use the calculator on the screen here. I've been using one in my hand for a bit. You can't see that as well. So let's clear that. And oh, I've got a pen in my hand trying to write on the calculator. Here we go. So clear that and get rid of that thing. Oh no, what did I do? Delete. I think my computer is struggling here. Might have to go back to the handheld one, unless I just move this out of the way. just a ink-aware smart notebook thing. Okay, here we go. 4.9. It's still doing it. Go away. There we go. I had two of them, I guess. So 4.9 and 4.9 times cosine of 30. So I have to do, I don't like this calculator because it's going to want me to do cosine of the 30, right? Yeah, I got to do that first. I don't like these kind of calculators where it's not the direction I think of it as. So I want to do 30 and then do cosine of it. So now I have what cos 30 is times the 4.9. Way harder than it should have been. 4.243. And that's whatever in newtons there. And so we've got our FGY, the up is the 4.243 number, and of course then the normal force. And so the, in fact, I'd be putting that in as a negative, I guess, because of the way we have things there, right? So that's down of the 4.23, and then I'm going to add that to both sides and get the normal force is up the 4.243, right? Again, that's going to be necessary later, right? So instead of the full gravity force, Mr. Anderson's full weight of 4.9 newtons, instead it's only 4.243. Right, so you can see how that's going to relate when we go back to that. This is the part that I was going to warn you of earlier by accident here. They, in the old online version of the content, which I'm clearly not just using anymore. So the net force they show is, obviously there's the normal force, the friction force, and the gravity force. So you're just looking at this overall picture, and you have these three forces: the normal force, the normal force, the gravity force, and the friction force. And you're just adding those together vectorially. But man, these vector signs here are doing some pretty heavy lifting concept-wise, right? You can't just add those up. You know, if the numbers were 10, 20, and 30, you can't just add them up. You gotta get what I do there, 60. You can't just add them up and get 60, right? So it's very dangerous to write that because they're all at angles. And so they say that in the online thing, they're non-collinear, and so we have to componentize them. But man, I would imagine there'd be a lot of students that would just look at that diagram, that FNet, and not realize the significance of those little vector bars and realize the angles matter a lot. So I'm just going to skip the rest of that part. But so question number 1, I think I'll just skip the answer, you know, somewhat of an answer from the online thing is there. Let's look at the question number 2, though, a little bit more. Question number 1 is just on a level ground. It's not even an inclined plane thing. Just left it in there because why not? But so we have a 0.30 kilogram book being pulled up an incline with a string that's parallel to the incline, makes an angle of 40 degrees to the horizontal, the angle of the ramp. The tension force is 5 newtons and the force of friction is 1 newton. Determine the normal force on the book, determine the net force acting on the book. Very similar stuff to what we just did, right? So free body diagram here, we have a gravity down, you have the y component of the gravity, you have the x component of the gravity, tension force, tension force pulling it up, and the friction force working against things, right? So they're going to analyze this out. I wouldn't put the negative in, but they're doing what I was saying about just with numbers, right? So this would go in as a positive number, this would go in as a negative number. It's down, right? And they're doing the same thing where the net force in the y direction is 0 because there's no motion vertically up or down relative to the ramp. Perpendicularly up from the ramp and into the ramp is not happening. Anyway, so they do the same kind of work. I'll just leave that one, I guess, because I think I've covered enough. Let's go back to Mr. Anderson here. So let's see if how accurate things were here. So we have a 17-degree ramp angle, and so we want to confirm that reduced force on the scale. So let's just use, we could do the calculations with newtons, but then I'd have to convert back to kilograms and then back to pounds, right? Double conversions. So let's just use the 172, right? We know this is 172 pounds. So this is FG 172.0, but unfortunately in pounds. So like, don't show anybody this. Like, I'm not doing physics in pounds officially normally. But yeah, we have that. And then we have the angle of the ramp obviously there. And then we're going to have the component, the vertical component. We're making a right triangle there, right? And then you have the horizontal component down the ramp. So all we're really interested in is this vertical component, right? We have our direction system like this, where we have the X and the Y. So we're doing a Y direction analysis, right? And so really here, we're just going to say, okay, well, FGY is what? Well, that 17 right here, that 17 translates to be this 17 right there. And so we're looking at an adjacent side, right? And so we're going to be looking at the 172 cosine of the 17. So we calculate and see what we get. So cosine of 17, oh, forgot the way this calculator works. Cosine of 17 is 0.95630 and so on. Multiply by 172.0 gives me 164.5 or so. 164.5. And that's again in pounds. Again, I could have done it in newtons and then go to kilograms and then go to pounds. His scale said 163 almost, right? 162.6. So slightly off. But if we were to do a calculation of percent error and so on, that would probably work out to be pretty small. It's pretty close, in other words. The other way we could do things is we could say, okay, well, if this number right here, if this number here for the Y component, which we know is the same as that normal force, right? Really the normal force reading, right, on the scale was 162.6. 162.6. Nice. I put newtons by accident, force of habit, but it's pounds, right? And so really this thing's equal to that as well, right? So FGY must be equal to that opposite. And again, that's based on the acceleration in the y direction, 0, and so on. Same analysis as always. We've just done it enough times. I think we can just get the answer done here, right? So we've got this unknown, this known here. This force is 172 normal force of gravity in pounds, of course. And we've got the known component as well. What we know is that FGY would equal full FG times cosine of the angle. And it's the angle we don't know in this case, right? If we're trying to confirm the angle, that is. So we put numbers in. We've got a 172.0. We've got a, apologize here, the 172.0 is the gravity itself. So let me go down a little bit here, 172.0, cosine of theta, right? So that's my FG. And then my FGY component is that reduced 162.6. So, we can see how far off the angle is from what it must have really been, kind of thing. So we're going to divide both sides by 172, or 170, sorry. It is 172. Oof. You can see people watching the video going, it's 172, but you can't tell me. Painful, right? So I caught it just in time here. And so we have cosine of theta equals that number. So 162.6. Just a double check for sanity here. 172. Yep, we're good. All right, so 162.6 divided by 172 is that, right? And then I'm just going to do cosine inverse of that. So trig, second cosine inverse, and it gives me 19 degrees. So the angle was really at about 19 degrees if we're trusting the scale, or the scale's a little off if we're trusting the angle, right? Not off by much though, right? 17 degrees, only off by 2 degrees. Yeah, I think that's a survivable amount of error for that little demonstration that he did. So good job, Mr. Anderson. I like it. A neat little way of giving the idea of like components of forces and so on, and relating inclined planes. So very much approve. I like it. So your questions, like I said, there's a little bit less here. Friction's given to you as a value, so you're not worried about components of friction yet. Yeah, so draw free body diagrams, calculate stuff, and so on, and let me know how it goes. All right, here we go. Until next time, don't forget to like and subscribe.